Yes.
Yay! Thank you very much for helping out here. All right. So what I was mentioning is that we started at the beginning of A with a very flat line, a very flat slope. So because of that, we know we're not changing very much over time at all. So our velocity must be 0. Flat lines mean 0 velocity. Okay? And then the slope increased. It became steeper in the positive direction. So we have an increasing positive velocity. And that's section A. At B, it's no longer changing its slope. It's maintaining a constant positive slope. So because of that, we have a flat line at B because it's a constant slope, so it's a constant velocity. And then at C, we start with a positive velocity, positive slope, and it moves to a 0 slope. So that must mean that it has to move in the negative direction till it hits 0. Again, a flat line over here means 0 velocity over here. Now, slope on a position time graph gave us our velocity. It told us how much the position is changing in a given amount of time. On a velocity time graph, the slope tells us how much the velocity is changing over time. So our slope is now going to give us our acceleration, where it is going to have meters per second squared. That's our acceleration. So again, that's the slope. How much we're changing our velocity in a given amount of time is our slope and is our acceleration. And then something that if you finished up the lab, you may have noticed, so I may be burying the lead here, but the area on this velocity time graph is going to be our area on our velocity time graph is going to be our delta x, or our displacement. And I want to talk about why that is. And this is really important. This is something College Board really likes to ask about, is knowing on a velocity time graph that the area is the displacement. If we look at just the area of A, so I'm going to say area of A is a triangle. So it has an area of 1/2 the base times the height. That 1/2 is just going to be 1/2. The base is time, so it has units of seconds. And the height is velocity, so it has units of meters per second. These are going to cancel out, and I get units of meters, which are the units for displacement. A good way to remember that. Okay? And I'm going to make it a little bit more clear by kind of filling in. The area I'm talking about is the area between the graph and the x-axis. Is that area here. So this area is going to be the displacement. On a scale of 1 to 5, how well do you understand this now? 1 being I don't get it at all. 5 being I have a pretty solid understanding. of it. Okay. Wait on just a few more people, and then I'll move on to acceleration. Again, I want you in the 4 range by the end of today in the lab. So if you're 4 here, that's good. Then you can move to 5. All right. And I'll talk more about this later. All right. Then I'm going to move on to acceleration. You probably have not seen an acceleration time graph yet too much. In the lab, you've seen one, but not too much. So acceleration time graph, again, we're just going to use slope to go in this direction. So the slope is, in this case, a positive slope. So that means we have a positive acceleration for A. In B, we have a very flat line. It is a 0 slope. It's going to be right here. This is B, and this is not to scale, but I'll label it. That's B. And then C, we have a downward facing slope. This is our first downward facing slope. But if it's downward, the steepness is downward. So we must have a negative slope. We start with the positive slope. We get flat along here, and we end up with a negative slope. Now, there's important information here, but they won't ask you about an acceleration time graph nearly as much as they'll ask you about a velocity time graph. But the slope is something called jerk. If you want to call someone the slope of an acceleration time graph or the derivative of the acceleration time graph, that's totally fine with me. And then the area between the graph and the x-axis is actually going to give you the change in velocity, how much it has changed its velocity the entire time. Over the course of the whole time period. So generally speaking, if we're going position time graph to velocity time graph, we use slope. If you want to go velocity time graph to acceleration time graph, you use slope. If you want to go from area to information about velocity, or sorry, acceleration to information about velocity, you use the area. If you want to go from velocity to information about the position, you use area again. Okay? Generally, now, 1 to 5. Give me in the chat how well you understand it for acceleration time graphs. Sped up a little bit on this one. 1 to 5, where are we at? Okay, a little bit more confusion, but some people are doing okay. Okay, like I said, I want you in that 4 to 5 range at this time. For the people that weren't quite there, I'm going to spend a little bit more time just talking about slope fundamentally and how we're using it for as long as you'd like. For anybody who feels really good, you can move on to finish up your lab, the Moving Man lab. I'd like you to have that done by tomorrow. If you finish that up, please do the check for understanding. That'll give me good information about how well you get this and what I need to review tomorrow. I really like us to be pretty solid on graphs before we really move forward, because we're going to use them quite a bit. I use them in the video. If you've finished up both of those things, the Moving Man lab, and you have finished up the check for understanding, please watch my Edpuzzle video. It's longer than I want it to be. It's not terrible. I think it's 20 minutes or so. But it's a little longer than I wanted it to be. I think it's pretty solid, but it's longer than I want it to be. So you can start that, which will be due Thursday. Are there any questions before I release some of you to work on the lab or to work on the check for understanding or red puzzle? Any questions?
No, I'm good.
Okay, party people. Then you do you. And anybody who wants a little bit more explanation on that, I'm going to switch back over to my document camera here and explain a little bit more. All right. So
Should I leave now?
it's completely up to you, good sir. If you want to stay and hear a little bit more about these graphs, you can stay and wait, or you can work on the lab.
I'm gonna leave.
Okay. See you, Dave.
Bye.
All right. So I'm going to talk about, I think position time graph is the most confusing for people. They ask the most questions on the velocity time graph, but the position time graph is the most confusing because it's that changing the curves. This is where you're going to see the most curve, and you're going to have to remember that we're looking at the slope. The most important part of a position time graph is going to be the slope. So I'm going to talk more about the slope. So slope in general is just, rise over run, or thought of differently, it's change in y over change in x, how much you've changed in the y direction divided by how much you've changed in the x direction. So on our y-axis, we have position. On our x-axis, we have time. And it should be starting to move into your head that change in position and change in time is velocity.
Mr. Chairman, I have
Yes,
a question.
Yeah.
So these notes, and are they going to be like on the stream or the classwork, or do I have to write them?
I will put them in there. Yeah, I can put them in there.
Oh, okay. And
Okay.
on the exams or quizzes, are you going to give like the formulas to us, or to memorize them?
Some of them. And I think anything take home, you'll have whatever you want available to you. But there are some equations, some formulas that I will give to you, and others that I will not. Because the ones that I will give you are the ones that College Board give you.
Okay.
Okay? Good question. So we know that our change in position over change in time is going to be our velocity. So if we're looking at, again, the slope, we need to look at steepness of the slope. The more steep it is, if it's here, it's going to be like a zero slope. If it's very steep at that time period, say we have this time period here, we look here, it's just now starting to get a little steeper. So that time period there is going to be where it's just starting to become a larger velocity. And then over time, by the time you are done with this place here, where A becomes B, these two sections meet, that's going to be this right here, where it stopped getting steeper. It's now just going to be a constant velocity. And because it's a constant velocity, we're going to have a nice constant velocity here. Constant slope equals constant velocity. That's a good thing to keep in your heads. And then you know, if say if this was a car driving, you know, this would be a car driving, starting right here and ending up right here. During this time, this is you hitting the gas and getting up to speed. Then say you're traveling, you know, at the speed limit around your neighborhood. Always a good idea. Speed limit being like 25 miles an hour. This would be the cruise control, or you just staying at 25 miles an hour. And then you come to a stop sign and you must stop. So you have to come from 25 miles an hour to a slope of 0 miles an hour. So because of that, you have to slow down. So your slope would go from 25 to 20, 15, 5, 0, where you're stopped. And that's generally what's being shown here. Remember, slope is always velocity on a position time graph. You have to speed up, start at 0, speed up to 25, go 25, and then come to a stop. In reality, you would be doing it like this. Speeding up to 25, so you stopped here, started here at 0, sped up to 25, go constantly at 25, and then slow down to 0. That's what it would be. Does that clarify anything at all? I'd like you to drop in the chat again, 1 to 5, how well position time graphs make sense at this point. Cool. Cool. I'm just looking for positive growth. Cool. Now, I think people were doing okay on the velocity time. I'm just going to say, again, the slope here needs to match the number here. Whatever the slope is here must be the number here. If the slope is 25, this must be at 25. And then if the slope is 0, this must come down to 0. And then again, the displacement can be found by the area where you are multiplying if it's a triangle, 1/2 base times the height. If it's a rectangle, it is, the velocity times the time. And you could think about that too. If I were going 25 miles an hour and this time was 1 hour, then it would be 25 times 1, and I would have gone 25 miles. If it were 25 miles an hour and it was for 2 hours, then that would be 25 times 1 plus 25 times 1, or 25 times 2 hours, 50 miles. You go 25 miles an hour for 2 hours, you've gone 50 miles. Then this is coming down to 0. I'm going to talk about acceleration a little bit. This is maybe the most confusing part. If you have an acceleration or a velocity that is moving away from 0, you must have a positive acceleration. You're speeding up here. Here, we do not have an acceleration. The acceleration is 0. So it's here. And then here at C, we have a negative acceleration because you're moving towards 0 in this case. Got to slow down, moving towards 0. Now, at this point, I want you to drop one more 0 to 5. Tell me, 1 to 5. Tell me how